Hello everyone. Today we will learn about titration, percentage yield, and percentage purity. The learning objective of this lesson would be identify and calculate limiting reactant or limiting reagent, percentage purity, and percentage yield. Titration. Today we will explore about one volumetric method in chemistry called titration. Okay, please take a look at the picture. There are balancing stones, with the plates and also the larger stones. On the other side, there are smaller stone, 4 pieces of smaller stones. Okay, let's say this is if we take analogy from titration to this picture, the measuring is basically by balancing the scale. So object with unknown weight is placed in one side of the plate, and object with known weight or standardized weight is placed on the other side of the plate. And then we can see the balance with the indicator. For this case, that the lever are level or straightforward, or level. So we can see here, or we can say that the larger stone equals to 4 smaller stone. Okay, similar to that, titration is also balancing the amount with equal amounts of known concentration. In titration method, the object with unknown mole or concentration is placed in a conical flask, and then we add something that we already known the concentration, drop by drop, until it balanced. How do we know it is already balanced? We use indicator. In this case, for titration, there will be color change. Okay, so by definition, titration or titration or volumetric method is a laboratory method to find the concentration of a substance or the analyte by adding a solution of known concentration, we call it the titrant, from a burette until the chemical reaction is complete. It is signaled by observable change called endpoint. So basically, the step-by-step of titration, that we pipette an analyte. Let's say the acid solution is the analyte, and then we add the indicator. So basically, the indicator will change in one condition to the other, especially when the condition is already balanced. The amount of analyte and titrant is already balanced. The titrant is held in the burette, and then there are valve to open it, so it will get inside the conical flask drop by drop. As the color change, we stop the adding of the titrant. So it signal that the reaction is already balanced, and then we can see the reading. We can subtract the final reading with initial reading to find out how many volumes of titrant needed to neutralize the analyte. Basically, if it is titration of acid-base solution, it actually indicates the same amount of H plus ions and OH minus ions. So the analyte will be in the burette, or sometimes it could be the other way around. So The solution in the titrant solution will be added slowly, and then uh, until we achieve the color change permanently. Yeah, so there are permanent color change that indicates the endpoint. Equivalence point is when the amount of H plus ions equivalent with OH minus ions, but the color still doesn't change. So we need one more drop for the color to change permanently. That's what we call endpoint. So at this endpoint, we assume that even addition one drop is only negligible. Yeah, so the amount of excess titrant is negligible to the calculation. So we just assume that that volume is actually equivalent point of the reaction. Acid-base indicator is basically a complex organic molecules, such as this one is phenolphthalein indicator. So there are acidic form, yeah, which is it doesn't change from pH 1 to pH 8.2, and then if the structure change because of the pH change, so it turns into pink. Yeah, the range pH is 8.2 to 12, so the ring open and then it will become pink. Okay, so basically the range of color phenolphthalein, it would be colorless from acidic to neutral, and then it would be pink from neutral to alkaline pH. So as I mentioned before, equivalence point equals to theoretical point in titration, where the amount of mole of titrant is added exactly enough to completely react with the analyte in the solution according to the balanced chemical equation. But this equivalence is cannot be observed because the color of the indicator still doesn't change during this equivalence point. So we need one more drop to change the indicator to turn color, and then it reach what we call endpoint. This is the endpoint of titration, where an observable signal, usually color change of indicator, shows that the reaction is complete. Okay, titration calculation. Let's say the reaction X A plus YT to forms P. Yeah, let's say X is the coefficient of analyte, Y is coefficient of titrant, and A is analyte, and T is titrant. Then P is the product. So there will be a ratio X over Y times titrant equals to N of analyte, or moles of analyte. So if we describe, if we change it into a concentration and volume formula, so X over Y times concentration of titrant times volume of titrant equals to concentration of analyte and times volume of analyte. So at the end, the final formula would be concentration of analyte equals to X over Y times volume of analyte over titrant times concentration of titrant. Okay, this is the real example of acid base. So if acid react with base, it always forms salt and water, and then NaOH plus HCl forms an ACl plus H2O. So in this case, X over Y times N NaOH equals to N HCl. Because the X and Y value is 1, so I put it into the formula and then change the mole into concentration times volume. So 1 over 1 times C NaOH, phi NaOH equals to C HCl times phi HCl. So we can calculate the concentration of HCl equals to volume of HCl over volume of NaOH times concentration of NaOH. Okay, this is the step-by-step acid-base titration or calculation. First, the data from the question, usually volume of analyte, volume of titrant, and concentration of the titrant. Then construct and balance the chemical equation. Calculate the average titrant. Sometimes the titration is done multiple times, let's say duplo or 2 times, or triplo 3 times. And then calculate the concentration of the analyte using the formula. Okay, let's see the example 1. A 25 centimeter cube unknown concentration HCl solution was titrated triplo or 3 times by NaOH 0.1 mole per decimeter cube. The result were 30.9, 31.1, 31.1 centimeter cube respectively. And then calculate the concentration of HCl. Okay, from here we can construct the chemical equation, balance it. So if it is already balanced, we can proceed to calculating the volume of the titrant. Yeah, the titrant would be the average volume of the data, so it would be 31.0 centimeter cube. We can use this volume to calculate the concentration of HCl because all of the data is given. So concentration of HCl would be 25 centimeter cube and then convert to decimeter cube, and then 31 centimeter cube convert to decimeter cube, and then times 0.1 mole decimeter cube. So the result would be 0.08 mole per decimeter cube for the concentration of HCl. Example 2. A 10 centimeter cube unknown concentration of F2SO4 solution was titrated triplo or 3 times by NaOH 0.5 mole per decimeter cube. The result were 22.1, 21.9, 22.2 centimeter cube respectively. Calculate the concentration of H2SO4. Okay, first we construct the chemical equation, balance it. So this is the balanced chemical equation, H2SO4 plus 2 NaOH to form Na2SO4 plus 2 H2O. So the volume of NaOH would be calculated, the average, so it would be 22.1 centimeter cube. And then for concentration of H2SO4 equals to the ratio, which is 1 over 2 times volume of H2SO4 divided by volume of NaOH time of concentration of NaOH. So if you put the number, you can get 0.11 mole per decimeter cube of concentration H2SO4 solution. Okay, let's do some practice. There are this equation. If you want to do your practice, pause the video, do the question, and then let's see if your answer match with the answer of this question. So the question is 20 centimeter cube unknown concentration of HNO3 solution was titrated triplo or 3 times by KOH 1 mole decimeter cube. The result were 10.8, 10.7, and 10.8 centimeter cubed respectively. Calculate the concentration of HNO3 if the given reaction as displayed, and then we can find the volume of KOH by averaging these three data, and then to get 10.8 centimeter cube. Concentration of HNO3 can be calculated this way, and then we can find that the concentration is 1.85 per mole per decimeter cube. Okay, practice 2. Okay, this is the question. You can pause the video and then calculate yourself, and then let's check your answer with my answer in this slide. Okay, we have question 10.0 centimeter cube of unknown concentration of calcium hydroxide solution, and then titrated by triplo by hydrogen iodide 0.6 mole per decimeter cube. The result were 32.5, 32.5, 32.4, and then 32.4 respectively. Calculate the concentration of calcium hydroxide, and then the given reaction would be already balanced 2Hi plus CaOH2 to form CaI2 plus 2H2O. Then the volume can be average, yeah, to get 32.4 centimeter cube, and then the concentration of CaOH can be calculated this way with the ratio 1/2, and then at the end we can get 0.09 mole per decimeter cube for the concentration of CaOH. Okay, you can find virtual titration for your practice within these two links. Yeah, there are gizmos, but this is you need to register, and it has 30 days trial, and the second one is free, but yeah, you need to try by yourself. Yeah, it's a bit complicated. Okay, let's move on to the next topic, which is percentage yield. How to calculate percentage yield? Determine the theoretical yield. Use the balanced chemical equation and the amounts of reactant to calculate the maximum amount of product that could be formed. This is called theoretical mass. And then measure the actual yield, do the experiment, and then measure the mass that the product you actually obtain, and then apply the formula, divide the actual yield by the theoretical yield and multiply it by 100% to find the percentage yield. So the formula would be percentage yield equals to actual mass divided by theoretical mass times 100%, and then this value is percentage, indicate the success of your reaction, with common reason for yield less than 100%, including incomplete reaction, product loss during purification, or there are side reaction. This is the example 1. A 20 centimeter cube of HNO3 1 mole per decimeter cube solution reacted with 20 KOH 1 mole per decimeter cube. And then we construct the chemical equation, balance it if it is necessary, and then after evaporation to dryness, the KNO3 crystal obtained was 10 grams. Calculate the percentage yield. So the actual mass is already given. We need to find the theoretical mass. So mole of KNO3 would be concentration times volume, which is 1 mole per decimeter cube times 20 centimeter cube. So it's equals to 0.02 mole by converting centimeter cube to dm cube as well. Yeah, we do the same thing with the KOH. So you will get 0.02 mole because the coefficient is 1. Yeah, we can divide. Actually it's the same thing. So basically there are 0.02. So because the value is the same, so it means that both are limiting reactant. So we can say they are in stoichiometric ratio. Okay, we have this equation. We already know that they are both limiting reactant. It is optional for you to put it into ice chart, but I prefer to do it. So I put it in the ice chart. So in the beginning we have 0.02 of KOH, and then they will react because both of them is stoichiometric ratio, and also both of them would be the limiting reactant. So at the end we have the product as the same, 0.02 KNO3 and then 0.02 as water. So at the end we will have 0.02, and then the sample is dried, so the mole of KNO3 is obtained 0.02 mole, and then we can find the mass by multiplying by molar mass. So we can get 2.02 grams. So the percentage yield can be calculated by dividing the actual mass, which is 1.89, and then divide by the theoretical mass, which is 2.02 times 100%. So it's 93.56%. This would be the practice for you, so you should pause the video, do yourself, and then continue the video. So there are 100 centimeter cube of PbNO3, 0.5 mole per decimeter cube, and then reacted with 300 centimeter cube of NaCl, 1 mole per decimeter cube, and then it forms a crystal of PbCl2 as a solid, and then we can obtain the crystal by evaporation to dryness. Calculate the percentage yield. So first we calculate the moles of PbNO3 by multiplying the concentration and its volume. We can get 5 times 10 power of negative 2 mole, and then for NaCl it's 3 times 10 power of negative 1 mole, and then divide by its coefficient. So we can get these two numbers, and because this is smaller, 5 times 10 power of negative 2 is smaller than 1.5 times 10 power of negative 1. So this would be the limiting reactant. So PbNO3 2 is the limiting reactant. And then we can put it on ice chart. Yes, so 0.05 and 0.15, and then because PbNO3 is limiting reactant, so it's used up, and then we are calculating based on the ratio to find the mole of NaCl that reacted, PbCl that produced, and NaNO3 that also produced. So at the end we have 0.05 moles of PbCl2. We use this data, and then we find the mass by multiplying by its molar mass, So we get the actual mass 8.9 grams, and we can calculate the percentage yield. So it's 89.89%. Okay, next we will learn about percentage purity. It's a bit different with percentage yield. In percentage yield, we calculating the expected result, which is the theoretical mass, and also the actual result. While this one, we determine the content of some crystal or some samples at the end by certain method, and then we calculate back theoretically how many in the samples, and then we divide by the total mass of the sample, so we can get the percentage of purity. Okay, first identify the mass of pure substance. This is the amount that calculated in your sample, and then determine the total mass of the impure samples. This is the overall weight of the mixture, including the pure substance and any impurities, and apply the formula so we can get the percentage purity. So basically, percentage purity is a fundamental concept in chemistry, as impurities can affect the substance in physical and chemical properties, making accurate purity calculation essential for various applications such as in drugs, materials, and food. So the formula would be mass of pure substance in sample divided by mass of impure sample times 100%. Okay, example 1. Let's say I have 5 grams impure NaOH is diluted to 100 centimeter cube of distilled water, and 20 centimeter cube of this solution completely neutralized by titration with 30 centimeter cube HCl 1 molar per decimeter cube. So we construct the equation, we calculate the mole of HCl, yeah, and then this moles amounts is actually same as the moles of NaOH. Because we perform a liquid from the total solution, and then we need to calculate back the number of moles by multiplying it by dilution factor, which is 100 over 20, so it's 0.1 mole. From here we can calculate the mass of NaOH, so we get 4 grams. But the sample of impure NaOH is 5 grams, so we can calculate the percent purity by dividing the pure substance divided by impure substance times 100%, so it's equal to 80%. This is your practice. Please pause the video, find the amount of your from the question, yeah, and then solve it. Okay, so the answer of the question, the calculation is similar from the previous one, so I will skip it to the end of the result, so it's 98.19. You can read more by pausing the video. This is your practice too. Yes, so please pause the video, solve it first, and then we can continue to discuss the result of the calculation. So at the end, the percentage purity of NaOH is 96%. Okay, thank you very much for watching my video. Don't forget to like, subscribe, and comment. Good luck with your study. Thank you very much.